Okay, I've put a fail-safe instruction in. I noticed a lot of times when I reset the computer, it resets to FF for the instruction. And right now there's just a bunch of zeros there and it doesn't do anything. So I programmed a special FF instruction, which is my fail-safe instruction. The FF instruction first takes the bus, which is normally at a low state, so it's 0. It puts that into the program counter, so it will 0 the program counter. It will then do 14 no-ops, so it's waiting to the very, very last microcode, and the very last microcode is to stuff also the blank address bus into the instruction register, so it will place a 0 here. So it starts with FF, it shoves a 0 here, it waits, it shoves a 0 in here, and then it should start up again. Let's try a reset. Nothing there. Of course it's not. Of course it's not going to cooperate. Oh dear. There we go. You saw it started with an FF, and then it stuffed in a 0 and it executed correctly. Now a lot of times it'll execute the 3 instruction, it'll do the jump, and then the very last time it ends up defaulting to an FF and it just kind of hangs. But now the FF is a failsafe and it'll like reset things and it'll start up again. So let's see if it does that. No. It does sometimes. There's something really screwy with the increment, the PC increment. There's a double glitch. There's a something funny going on there. There's some kind of condition I just don't know where it's coming from yet. Here's the 3. It's going to execute it the second time. Alright, let's see if it executes a FF next time. There we go. Oh, it didn't. It executed a 15. Not a FF. Oh, interesting. Oh, that is 15 here. It's showing 16 here. That was 1. I don't know. I had it working such that... There we go again. It started with FF and it started up. Anyway, so I've got at least one failsafe in there now. Sometimes it will actually loop around when it hits that failsafe. But there's obviously something strange going on with the PC increment. We'll have to get to the bottom of that. Once we get that figured out, it should operate pretty good. I don't know. Anyway, it does make it easier to reset. There we go. Try it again. Power it off. Power it on. There we go. Oh, interesting. It doesn't always work. My failsafe doesn't always work. Yeah, there it was. You saw the FF here, and then it started up again. So anyway, having some codes in there to catch some funny conditions is probably a smart thing to do. A lot of times what you'll do is you'll actually catch that FF and halt the processor. So a real micro, like the Zeta 2 actually has a halt line on it. There's 2 LEDs. There's a run LED and a halt LED. So if it gets hung up and it gets into a strange condition, it's smart enough to know to halt itself. And we should be able to build that into this eventually sometime too. Okay, going back to the 22V10, I have an idea. So we have a signal that's PC increment, and PC increment is a low going pulse. It comes out of an LS154, so it's a 4 to 16 decoder. And so when 4 bits of the microcode instruction gives you a from and gives you a to, 4 and 4. And this is a PC increment. And that's what's being sent to the 193 chip, our counter. And somewhere there's a glitch. I don't know if the glitch is on an edge. I don't know if the glitch is maybe somewhere else when there's switching. But there's a glitch somewhere. And that's causing a problem, so it's doing a double count. And for whatever reason, if we divide this by 2, it goes away. I don't know why. But we need to clean it up somehow. The divide by 2 is not a great solution. The divide by 2, if you had, if the PC increment was going low, and then you did a double count, and then the divide by 2 would basically be, it would change on that edge, and then it would change on this edge, and it would end up being a square wave. And what we want is a pulse. So this is not working right, and that's what we see. So what I want to do is clean up the PC increment. And the way I'm going to do that is I'm going to have PC increment, which is a from device. And remember, we had a to device, and the to device, we would always select a from device, and then we would select a to device, and the to device would cause a clock between, and so the from device would be asserted on the bus, and then the from device would actually clock. And so you can kind of think of these two things actually have to happen in order for this to work. And we might be able to use that to clean up our pulse. We have a from pulse, and if we can find another pulse and these together so that we're only looking at a particular point in time along this low, that we're only saying we want to know that it's valid in this region, and it doesn't matter if it glitches over here or glitches over here. We're really only looking in the middle. Okay, so that's what we're going to do. And I'm going to use, since we have a 22V10 that's completely underutilized, the 22V10 basically brings in a clock from the 555 and generates a two-phase clock, and then that goes out. But there's a whole bunch of pins left over. And so what we're going to do is we're going to use the 22V10. Right now, pin 1 is where the clock comes in, and pins, I'm using something like pins 18, 19, and 20 or something like that to bring some clocks out for the two-phase. So I'm just going to choose some pins. I'm going to choose pin 2 as a input, and I'm going to pin the right across pin 23 as an output. So we're going to come in pin 2 and we're going to go out pin 23. And what we're going to bring into pin 2 is PC increment. And what we're going to come out of PC pin 23, we're going to send back to PC up, or I guess up on the program counter up count. Right now we bring the PC increment directly to PC up, but we're going to route it through the 22V10. Okay, so what are we going to do logic-wise inside here? We're going to have to add two statements to our program, our when couple program. We're going to have to declare an input, so we'll say pin 2 equals, we'll call it PC increment. And then we're going to say pin 23 is going to be, we'll just call it, what did I call it here? I'll look across. I called it P5, just phase 5. P5. And then we're going to define P5. P5 equals, let me zoom in on this a bit so you can read it. P5 equals, okay, first of all, we're going to want to do some type of combinational logic between PCINC, which is pin 2, and we have a remember we have a from pulse, and we have the to pulse is actually kind of right in where we want to be. So we're going to use the to. So there's a phase one. That's phase one. Okay, so phase one. So we're going to do some combinational logic to say that we want the PC increment to be valid and phase one to be valid, and then we're going to AND these together and create a phase 5, which is going to be our new PC up. Okay, so we want to actually do an AND. So we will put an AND sign here. Now we want to AND positive logic. PC increment is a low going pulse, so we're going to need to invert that. And phase 1 is a positive, so we can do that. Okay, so if we did this, what we would get is we would get a positive going pulse when these two both were valid. And what we want is we want a negative going pulse. Okay, so we're going to invert that. So that's the only declaration that we'll have to make. This P5, which is PC up. In fact, we should probably call it PC up. PC up. And we'll call this PC up. PC up. That'll make it easier in the code. And so PC up is now PC increment and phase 1. And we'll try this out and see if that cleans up our pulse or not. Should be interesting. Okay, this is the when couple program that we were using before. So I've added a couple lines. I've added the this line here. Pin 2 equals PC increment. That's an input. And then the output we've added is pin 23, which is PC up. And this is what I've added here. PC up equals not, bracket, not PC increment, and P1, which is the phase 1 clock. And yeah, we can compile this and we'll program it and see. Oh, and then I need to wire it up. So that's going to take a while. I'll need to take it into the garage and hack another connector onto it, wire up an input and output, and yeah, some work, but hopefully it'll fix things.